Okay, so, let's continue. This is a lecture 2 for the course Advanced Non-Relativistic Quantum Mechanics. So last time we study a lot of mathematics point of view of the state, right, and as well as operators. So today we continue uh, on this topic, unitary transformation. Okay. All right. So this is the first topic for today. I believe that you, for sure, that you encounter with this kind of transformation before. Can you give me a kind of definition? What is unitary transformation or kind of unitary operator, something like that? Time evolution. Position transformation. Yep. That is a definition. Just examples. Okay, interesting. So, let's see what does it mean by this word unitary here. Okay. So we learn how to construct the metric representation, right? Last term. Of suppose we say operator A here. Now we going to consider the transformation behavior of these matrices when changing the representation. Okay. So what it means that if we start to use the representation, something like this, and so you later you change to a new kind of representation in this way, what we are going to do is to look at what really happened to this to the metric of the operator, something like that. So suppose that we have an operator A with a set of bases. I would say this one. Okay. Which satisfy this one. Okay. This is nothing but an eigenvalue equation that we mentioned last time. Okay. Then, so it's not difficult to see that actually this element of the operator A, right, can be written in terms of this. Okay. All right. I would say is the out rep of operator A. Okay. On the other hand, if we have this a new set of eigen equation where this is a set of bases, okay, for M here, okay. So then we also have, of course, that you can put the operator A in the matrix form by using this a new set of bases, okay. So you may call this the M rep of, yes, of course, that now what we need to see is that is the connection between these two things here, right? To do in order to do so, we start to expand the eigen function of M in terms of eigenfunction of A. Oh no, of L actually. Something like this. Okay. And so it's not, so you can say that this is the coefficients that you need to solve, right? So then you're going to employ orthogonality, right, of this basis. So what you get is that no. So here, so you put this, the compact conjugate of this one to the left hand side, and then you integrate all the volume. So what you're going to have is that this delta function right here. And by looking at this equation, so this delta function will select only one s, that m equal to n, right? So you're going to get, of course, then now you know what is the s look like now, okay? So the matrix element this is nothing but is called a projection of this state onto this one. Okay, I put the underline, yeah, the word projection right here. Do you kind of get what I mean by this word projection here? Did you say, can you explain?
In the basis M to basis
Yep. Mm-hmm. Yep. Okay. Can we visualize it? Is it possible to visualize it? I'm not really sure that you get my question right or not. But if you can think about this projection, is nothing but just a standard vector thing, that actually you have a vector, and that vector can be expanded in this set of basis, right? Like you can think in this way. So you have a vector, and so you get phi 1, phi 2, phi 3, right? And what we did here, so suppose this is phi m. So you did the projection from phi mu, so suppose this is phi mu. Then this is the way that I call projection here. That is the thing. Okay, make it simple like that. Okay, so, but, well, this is kind of cartoon way to make this visualizable, because as I mentioned, a set of this one is kind of can be finite or infinite. So you have like a vector's infinite dimensional vector space, right? But this vector space is very special. because it's not just ordinary vector space, you know, right? So let's continue. So once you get this formula, so you can now look at this. Okay. So what I did is just I start from this equation. Okay, and then I apply this relation here, right? And then I get that. So it's not difficult to see now. Actually, oh, sorry. Okay. And you know what this is, right? This is element, right? Okay. So now you can rearrange things. So you see that oh, sorry. I think it should be n here, right? Yeah, sorry. N, m. Okay. So we start with this and m and m mu. So this is the way that the metric elements of the operator A transform under the chain of the basis representation from the R to the M. Okay. And you know that actually NM is nothing but a dummy indices, right? You know the word dummy, right? Okay. It's not mummy, right? Dummy. Okay. Kidding. Okay. This means it can be anything, and it's not going to appear on the other side of your equation. So here is not a metric representation yet. This is just a transform from the element, this element to this element. But if you want to put in a metric form, so it's very simple. You just put this kind of bracket, and so mu n okay. That's it. Or so you can say in this way, right? What I did here is we start from the A operator in the L representation, right? And then you do the transformation by sandwich this metric S here. You're going to get operator A in representation of the M, right? Okay, any questions so far? No? Good. So, okay, so so we have a requirement that this one as well as this one must be autonormal, right? Eigenfunction and this implying the unitary of S here. And get too close to the station and should stay away. Let's see. Why do we have this unitary operator of the S if this one and this one possess autonormal properties? Okay, so you start with this. Okay. Yes, you have this, and then what you need to do is that, so you put transformation okay. And what you get is okay, you have this one, and then you know that actually this is nothing but a delta function. Okay, so it means that at the end, so this delta function will get rid of one of the summation, right? So at the end, suppose that you're going to take m away, so you're going to have n mu here. Which is actually okay in this way. Well, you know that actually when you look at this is nothing but a multiplication between two matrices, right? Because you have this summation of the n, which it can be treated as an internal indices, which is going to vanish after you finish your multiplication, right? And at the end, you're going to, what we left is that only mu and nu here, right? This thing. Very simple as that. So from this whole equation, so at the end, so you will get this relation here. Yes, because on this left-hand side is going to be 1, if and only if mu and nu, yeah, otherwise 0, right? And you get the identity metric on this side, so you get this equation, which is actually this unitarity condition. Okay. So the question is that this unitary matrix need to be Hermitian. Do they need to be Hermitian as well? If I give you this S matrix, which is actually satisfy this condition, that this matrix has to obey the Hermitian condition as well. Yes or no? Yeah, of course, no, yes. Okay. So we know that a unitary matrix is not necessary Hermitian, right? Because it's not necessary that this condition is going to be always satisfied, right? Okay, so this is a note. So what is the meaning by having the unitarity? What does it mean by having this? If you have a unitary matrix or transformation, this, well, actually you can think this all the thing that we did on the board so far is just nothing but transformation, right? And the question, why do we need this kind of transformation to be unitary? Because we do start from this way. Right, we start from this transformation, right? From one set of basis to a new set of basis, right? And it turned out that this element of the matrix has to satisfy this unitary condition. Why is that? You know? Sorry? Orthogonal? What does it mean by orthogonal? Any idea? This is very basic quantum 101. Well, I'm not, okay. Now I'm not going to say something like this is too basic, this is too easy, because I think this put a lot of pressure on you. Sorry about that. So, can you give me an answer? Why, why do we need this kind of unitary operator somehow? Mhm.
มันจะเป็นแบบว่าเตะมันจะมีโลไปจะมีโลไปไม่ต้องเปลี่ยน basis
Yes, and yes, yeah, that is a role of the S. Yeah, you change from one set of bases to another set of bases. But there must be a condition that you need to preserve information. What kind of condition that you need to preserve? Do you know? It has to be invertible. Yes. So, okay, so actually what we need to preserve somehow, okay, is the plot condition, right? Yes, which is actually 1. That is the reason why you need this kind of operator. Otherwise, it's not going to give you this pop condition. Do you believe? Well, understand one. So, well, if you put here, if you look at this product here, what you are going to get then? Yes. Okay, we can do it integrated. Of course, then you can do that. Of course. So this side you're going to get, and on this side, if you start from that, yes. So, well, I'm sorry. I should put this in palm because we use M already there. Then that's the N palm. So on this side, what do you get then? So you have summation of M and what? S N M and integration S, right, and no, it should be M palm, right. Yes, in this way, is this right? So basically, you're going to have okay. Is this make sense? I don't think so. Yeah, it should be M here. It should be M here. Yes. Okay. So you get rid of the M. So you're going to have this square. No, not yet. Not yet. Okay. M, N, N, M. Right. Yeah. So then you get 1. If in case that actually Mn is the same, right? And M. Okay. So, well, just I think it's better to leave in this way. So what you need is that, so on this side, what I'm going to do is that I put the summation n, right? So what I'm going to get is that what we left is only M, yep. Is that right? Yeah. No, I think it's something wrong. Something wrong. Oh, okay. Just sorry about this. Actually, what we did have here is that MN and M. And then, yeah, of course, then it's going to be square of N and N pi. Right, and then you get 1, okay? Yep, some N, so do I need to put summation N? Yes. Otherwise, be satisfied. Yep. Okay. I think that's now. So earlier it's called we need to do the summation n to get rid of the sum of this delta function, right? And then you left n only this side, and then you get this condition. So okay. So this is actually this equation, and this equation is exactly the same, right? Okay, so we have one more property that we need to look at. If you have this, consider trace of this AM. Okay. You know what the trace, how to do the trace, right? It's the sum of the diagonal, right? That is a symbol. And so, and then you change the representation to the L operator. Yeah. By employing this kind of matrix. So what you get is okay. And so here you get the delta function, right? So at the end you will get n, which is actually trace of this A on, yes, it's the same. This is called trace preserving property. Okay. Okay. So can you give me again example of the operation? I think you mentioned that earlier. Yeah, time evolution operator is one of examples, right, of the unitary operator. Anything else? Rotation? Oh, yes, of course. What? Sorry? Transformation operator. What kind of transformation you have to specify a little bit? But anyway, so well, that kind of example that we do have, and yeah, I'm going to give you a set of homework to work out. to check whether this set of operator they satisfy the unitary condition or not. So the next topic, S matrix. Okay. What we need to look at is the temporal evolution of the system which actually can be described as a series of unitary conformation. Okay. Called the S matrix. Or scattering matrix, probably. But we're going to look at this, I mean, the word scattering matrix later on in more detail. But this is kind of look at on this temporal side first. You know what I mean by temporal word, right? Do you know the meaning of this temporal word? Can you guess? Yeah, temporal evolution. Ooh, 11 โมงแล้ว Okay. Okay. So normally in physics we have two things that actually you have spatial and temporal. No, no. Can you? So suppose I have this wave function. So I say that actually now this S is a function of time. So this is, okay. Can you see now? What does it mean by temporal evolution? Yeah, it's nothing but a time evolution, right? Yeah, it's another kind of fancy word for the time. It's kind of temporal part. Yeah, spatial part, something like that, that kind of time evolution. Okay, so we start with this mapping. You can look at this as a mapping. Can you see? This operator acted on this state, and you get the new one at later time t. So yeah, it's nothing but the map. And this map has to be unitary map. It has to be unitary map. So suppose that this, I could not draw infinite dimension of the vector space, then this is represent our Hilbert space. Okay, it can be finite or infinite. So it means that suppose that so you have a vector. So okay. And so under this mapping, oh sorry, it's too long. So you need somehow to, but it's kind of, this is too cartoon somehow, because this kind of map to a new state, right? This is like, maybe this is origin, your space somehow, okay? So from this here, and then this is a condition. What does it mean by having this condition? Do you know? What does it mean by having this condition? I mean, this is T0 is equal to 1. What does it mean? Yeah, it's mapped to itself, right? Yeah. Correct. So from this, you're going to have the Schrodinger equation, right? Yeah. We should okay. You have this. Well, actually here it's this one, right? Right. You have an equation for this state, and then you use that transformation. Do you get this equation? And then you have to, then this equation has to override this. And then from this, it means that this equation holds if and only if you have this. Yeah. And can you solve this equation? How to solve this equation? Do you know? Yeah. This need to be determined. Okay, this S. So the question, how to do that? Do you know? Oh, okay. By what? You mean this is just very simple ODE, right? Yep. But this is the operator, right? Can we do that straight away? I mean, so we can think this to be and then you get what? So you get T. That's it. Any, well, it must be a constant, right? If you do the integration.
Yeah, it must be. Yeah.
Where is the constant?
In front of me.
This.
Yes.
And then how could we find the value of this constant?
Initial condition
Yes.
equal 0.
Yes.
Yes.
So you get 0 equal to that 1, yeah? Right. Okay. Correct. And so at the end, so you get this. Yep. And so it is not difficult to see that this satisfy this unitary condition, right? Actually, there is another way that we can solve for S. Okay, but I'm going to leave it as a homework for you. This is kind of straight way to do that, but anyway. Okay, so actually, this one can be expand. Yes, but you have to be careful because, yeah, the operator might not be necessary to be commute at different time. But that is, well, we're going to deal with that with this kind of thing later on. Not now, but I just mentioned that actually we can do expansion, and then you can put the time ordering operator, something like that. And so, but the thing is, so note what we did here. This does not depend on time explicitly. Okay, your Hamiltonian does not depend on time explicitly, but if it depends on time explicitly, so you're going to get something else. Do you know what it look like? Yes, if your Hamiltonian depend on time, so what you're going to get is kind of integration. This one, okay. And so I'm going to leave as a homework to prove this for you. Actually, if this Hamiltonian depends on time explicitly, you're going to get this kind of integration. And once you get, you do the expansion, that is going to be a little bit tricky. Anyway, so let's continue. For very simple here, actually your Hamiltonian doesn't depend on time explicitly. For example, harmonic oscillator, right? Harmonic oscillator. You know that your Hamiltonian is, and so yes, this one, right? This is, there is no time here in this equation, but it is kind of, the time variable is kind of hidden somehow in this variable somehow. That's kind of implicit way. Okay. All right, so now we focus on the energy representation in which this one and your complete solution at initial time. It's not necessary to be 0, but it's kind of easy for us to set the initial time to be 0. It actually can be any number, right? Okay. So, okay, so I'm going to add the operator that we have there on this equation. So what we have here is a here. This is not what happened to the microphone. Okay. Yeah, I can take like a minute not to breathe. And okay. Sorry. Actually, this is constant. So who is out here? Oh, sorry. Can you call Pijo? And I need to go to toilet. So take a break then. Can you help on this? Okay. Okay, I think it's better now. Here, what I'm going to do is that, so I do the series expansion of that exponential. So I'm going to get k factorial. This to the power k here. Right. And so since this the Hamiltonian operator, so it's act on this going to get eigenvalue, right? So what we have is that, I'm not sure, can you see it clearly? Because you have to put this in the series and then acting on this function to get E out of this. And finally, so what you get is that you get E here, which it actually depends on the which state that you're acting on, right? Okay. I'm not going to, well, I think you understand what's going on here, right? And then I not need to make it, put it into detail then. What's going on? Okay. So what we have here is, so we can put back that infinite series in terms of the exponential function here, right? And so you say that, you can say that all this whole thing is nothing but this one. Yep. Okay, simple as that, very basic stuff. And then next, if we expand this in terms of this, a new set of bases, okay, like we did earlier. You can do in this way. And so yeah. So this is kind of initial, right? And then you expand this one in terms of that. It means that somehow your coefficient has to be function of time. And once is the function of time, it can be put in this way. And it is not difficult to see that if you want to solve for this BM, you're going to get this one. Okay? Right, if you want to solve for this BMT, you can do it by, well, from this, I'm not going to divide for you, because I'm going to leave as a homework. It's not difficult, it's just 2 or 3 lines and done. Okay. Now, we consider a special case equal to 1. Yep. N here. Then for Bj, that actually are 0, right? There is only one B that survive by having these conditions. This means that in the LREP, the particle at time 0 is completely in the state okay? We may say that the system is prepared in the state, okay? All right. Like I given you this state as at the beginning, and then later on we see what will happen. Consequently, we're going to have this one. Here. You see, from this equation, because this is 1 there, yeah, right, from that, because this is a condition, right? When you sum over possible n, at least only one of them survive, right? So I don't need to put 1 here, okay? Soหิวข้าวแล้ว so SM and yeah, the amplitude with a system has passed over from state this into state this after time t. So I shall define this notation, this fancy p, as the amplitude shall define as a transition plop, okay, from to M under the influence of this Hamiltonian operator here. All right. Okay, let's continue. So now we're going to look at the Schrödinger equation in a metric form. Okay, so we start with this equation where this satisfy this eigenvalue equation. Okay. So this means that this can be expressed in terms of the linear combination of this eigenstate, right? But the thing is that, so as I mentioned, we can put the time of origin in the coefficients here. And so what we are going to do is that we put this back. So you put this back into this equation. So what you're going to get is that this one okay, you will get this equation. And so I'm going to employ the orthogonality condition. So I'm going to put this m dv integration, and on this side, so as flow. Okay. And so at the end, so what we're going to have is that you're going to have a dynamics equation for the coefficient A, right? So this is give you delta function, Mn. This is also give you delta function, Nm. So what we have now is this equation. Okay. And so you could solve for this one, which is actually not difficult, right? You can solve for this an, right? Which is actually, this is can be determined by the initial conditions. Okay. So next, we look at expectation value of any operator, but suppose that we look at for the L. So you're going to have this, right? So then, so what you're going to do is that you're going to apply this relation here, right here, put in there. You're going to put here and here. So what you get is a bit long, but it's not difficult to write it down. Let's see. So what we have here is that m star n L n I should be here. Right. And then dv here. So again, so what you're going to have is that Mn so where okay, this one. So this is expectation value of this operator out in terms of the metric form somehow. Okay, so next we're going to look at the time evolution of this expectation value. So you're going to do the derivative. uh, and so okay, so you're going to have these three terms out of this okay, I think I'm kind of correct. Should be yep. And then we using the fact that so you have this equation in hand. So then this equation is going to be some okay. So well, if well this is exactly the same equation, okay. Because what you need to do is that you just say that that's it, okay. Okay, so well, since you're Hamiltonian, this is the Hamiltonian element, right? Okay, or the metric element. So since is Hermitian, so it means that so this one, right? So then what you have is now okay. So you're going to have this. And so actually this, you see that actually this is a multiplication of the matrix, right? So this whole thing can be turned to this okay, in this way. So finally, what you're going to have is that and then so I can, well, I can pull out this thing, M, and okay. Oh, it should be K here. I can change because this is kind of dummy index, right? I can change to be anything. So, okay. Now I define this bit to be, so I put this total derivative inside the bracket. I'm going to have this, which is you can put in a metric way, in a metric form, like this, okay, which is represented by this whole thing. So it means that this means that now we have this equation, the metric representation of Mn. Okay, that's correct. Okay, does this look familiar to you guys? This is, you can say this is a quantum analog of the what, the classical thing that we should have here, like if you have no, okay, this, right, this is a Poisson bracket here, right, and L and H define on cotangent bundle. Yeah, it's a function that define on cotangent bundle. But anyway, okay. So what we have is this kind of thing. Okay, I think I'm going to stop here for today. So I hope that I cover up all kind of necessary basic math. Next time, we're going to start with the showing a picture, Heisenberg picture and Dirac interaction picture. And that's it. Any question? If not, then yeah, stop here. Thank you.